Hey guys, welcome to your first Chapter 22 stats video. I have time just to make one tonight. It's already, as you can tell by the clock in the lower right, getting a little late. So the second half of Chapter 22 will be published realistically Wednesday, 2 days from now. So be ready for that when it comes in. Chapter 22 does two things. Now that we have seen how to work with a confidence interval for a single proportion, where, again, just kind of refreshing what the confidence interval does for a single proportion, if I give you a sample proportion, and if certain conditions have been met, then we can use the normal bell curve to cast these nets that we call confidence intervals to try to capture the true population proportion. That's what the confidence interval for a single proportion did. We also used this bell curve to explain how samples would behave if we're given the population proportion. So going kind of in reverse from a confidence interval, if we know what the true population proportion is, how do we expect sample proportions of a particular size from the same population where the samples are captured the same sort of way? How do we expect those to behave as well? Those are the sorts of things we've looked at so far. Thankfully, in Chapter 22, we're not taking a big logical leap forward. What we're going to do is we're going to talk about today a confidence interval for the difference between two proportions. So we could talk about this is going to be a little similar to the example you're going to see next slide, but that would answer the sort of question like, okay, we've got a sample of boys at Yorktown, and we know from that sample what proportion of them endorse Mitt Romney as a presidential candidate. And we might have a separate sample from the same population of Yorktown students, only this time the sample is of the girls. What proportion of them endorse Mitt Romney as a presidential candidate? And we could talk about, by building this confidence interval, we're going to be able to answer the question of how do we believe the true population proportion of percent of all boys versus percent of all girls who support Mitt Romney to be. So if that difference is 0, then that means the boys and the girls think the same way. If we're describing our difference as the proportion of boys minus the proportion of girls, if that difference would come out to be a positive value, then that means that generally boys are more favorable of Mitt Romney, of girls. Well, that's true. And if this value of population proportion of boys who support minus population proportion of girls who support Mitt Romney was negative, that means the girls would generally favor Mitt Romney as a presidential candidate over the boys at Yorktown. So that's the sort of thing we're going to look at. Hope that explanation made sense. The conditions to use the normal bell curve, surprise, same distribution model that we've been using for chapters upon chapters now. The distribution, or the conditions to make sure the normal bell curve can describe a difference between proportions are really the same as we've been using for proportions in the past, but there are a couple of things that you need to pay attention to here. First of all, when you are looking at the randomization condition, if you're talking about two samples trying to get at a difference between population proportions from two different samples of different populations, then you first need to know, did each sample that you drew come randomly from the population? First thing. Second thing, 10% condition. Is each sample, and going back to the sort of anecdotal example I gave you guys a little while ago with support for Mitt Romney among the boys versus the girls at Yorktown, is the sample that we have of boys when we interviewed them for their support of Mitt Romney, is that less than 10% of all the boys at Yorktown? Similarly, is the sample of girls in asking their support for Mitt Romney as a presidential candidate, is that less than 10% of all the girls at Yorktown? So really the conditions haven't been different so far. You just need to be cognizant of the fact that you're checking twice for these things, for randomization, for 10%. But for independence, there is a little quirk here. Yes, as we've done in the past, you want to think in terms of, okay, so am I interviewing these boys or am I interviewing these girls in such a way that their opinions of the boys' opinions are not influencing each other, the girls' opinions are not influencing each other. But on top of that, you need to make sure that the sample of boys and the sample of girls also don't interact. So within the sample of boys, is there any interaction that we need to be aware of and the responses that we're getting? But also from the boys to the girls, is there any interaction in the responses we need to be aware of? If so, we need to make note of that in the independent section for the conditions. Normally, just like with randomization, the independence condition is not, at least within the book here, going to be such a hang-up that you can't move forward with a confidence interval for the difference between two population proportions. All right, last one here, success-failure condition. Again, you need to think in terms of this condition doubly. So your conditions are going to take about twice as long to check. It doesn't make them harder. It just means there's more writing, which I know you guys have been asking me for months now. Mr. Shelton, how can we take this class and strip away even more math and do even more writing? Because that's really what we enjoy. We didn't know that we were signing up for an essay course, but we love that about statistics. So good news, if you love the writing element of this course, you've got more of it. Success-failure condition. You need to make sure that, again, going back to that anecdotal example with boys versus girls' interest in Mitt Romney as a presidential candidate at Yorktown, you need to make sure you have at least 10 successes, at least 10 failures among the boys' sample. You need to make sure you have at least 10 successes, at least 10 failures among the girls' sample. Easy enough? Well, too bad. You can't respond to me in this video, so I hope so, and I'm going to move forward anyway. All right, so the normal bell curve here, bottom left, again represents the distribution for a difference between independent proportions as long as those 4 prior conditions have been met. That is going to be centered. If we're building a confidence interval here, the mean's going to be centered at the difference between my sample proportions, p hat 1 minus p hat 2, with a standard error, because when you're working with confidence intervals, you're trying to get at the population proportions. You don't have those to start with, so notice we're working with standard error, not standard deviation, of the following. This really, I don't think it's, looking at that now, I should just rewrite that. Let's rebox that below. So the same thing in that box, it means what I'm about to write. Square root of p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. Now, where this standard deviation came from is actually not too complex. That's something I could derive for you guys in class. I don't know that I will. We're a little pressed for time, and I think that it would be smart to try to get a test in prior to spring break rather than testing afterwards. So you may not see me derive this, but if we get some time, I'll do that for you guys. So those two box things mean the same. Notice that 1 minus p hat and 1 minus p hat 1 and 1 minus p hat 2, that just means the complement of p hat. Well, that is q hat 1, and that is q hat 2, here and here. All right, so that's your standard error. In essence, the standard deviation, so you move that far to the right here or to the left on this bell curve, two standard errors away from the mean, etc., etc. Your confidence interval for the difference between two sample proportions is awfully similar to the confidence interval for a population proportion if you have just one sample. Again, though, what this bell curve is representing, let me slow down and make sure that I explain this without rethinking what I'm saying here as I say this. This bell curve is explaining the differences we would expect to see between samples of, going back to that anecdotal example, differences we would see of all the same size, collected in the same way, between boys and girls. So again, if p hat 1 is the proportion, sample proportion of support we have for Romney among the boys, p hat 2, the sample proportion of support we have for Romney among the girls, anytime this, how to write this, anytime p hat 1 minus p hat 2 comes out to be a positive, that means p hat 1, or the proportion of support we have for Romney among the boys is greater than the support for Romney we would have among the girls. Conversely, p hat 1 minus p hat 2, if that comes out to be a negative, that means that p hat 2, support for Romney among the girls, would be greater here. Right? So this normal bell curve explains how sample proportions would behave, but from that bell curve you get the confidence interval right here, explaining what you expect the difference among population proportions to be. So notice your confidence interval. Let me erase some stuff so it's a little bit less cluttered here. Your confidence interval is centered on the mean, p hat 1 minus p hat 2. That's this guy right here. And then your confidence interval, the net, the margin of error, which we've worked with before, z-score times the standard error. That tells you, okay, for whatever the standard error is of this bell curve right here, how big a net are you casting? How big a net are you casting to estimate the true population proportion difference among support for Romney among boys versus girls? So obviously, if you cast a margin of error net with a z-score, let's see how to write that. So our confidence interval here, ranging from this low value right over here to this high value over here, would have a z-score equal to 1. You're not casting a very big net, and you would only be 64% confident in the true population proportion difference for support for Romney among boys versus girls at Yorktown. Obviously, if you go with a margin of error for your confidence interval that is at a z-score of 2, now you are 95% confident in the fact that you have captured the true difference in support for Romney among all the boys versus all the girls. All right, so there's sort of the theory. Let's jump into a problem in context and see if we can make sense of this. I'll show you how this works. It's not too far removed from what we've done in the past. All right, so example 1, to find out. Oh, by the way, before we do this, I was looking again over the stats reference sheet. On the back side, which we've only recently got to that content, and that's fine, we're moving at an appropriate pace. On the third section of the AP stat sheet, you might want to take a look at this with me. It's called Inferential Statistics. The standardized test statistics section is kind of useless, but the information they give you for single sample statistics is helpful. So they tell you in this gray statistic block how to find the standard deviation for a sample mean and for a sample proportion. You guys have been forgetting which applies when. You've got that freely available come next test, whether or not that's before or after spring break. The sigma over square root of n, they say, is appropriate for a sample mean. So if you're building a distribution of sample means, they've given that to you. If you're building a standard deviation of sample proportions, they tell you the square root of p hat, or excuse me, pq over n. Also, so the single sample stuff we've done, they also give you the standard deviation for a difference of sample means, which we will not cover until definitely after spring break, and the standard deviation for a difference of sample proportions, which I just showed to you, that square root of P1, Q1 really over N1, first sample size, plus P2, Q2 really over N2, the second sample size. All right, so that being said, just don't forget that you've got your standard deviations going into this next test provided for you on the stats reference sheet. All right, example 1. To find out who people think are more intelligent, men versus women, the Gallup poll selected a random sample of 520 women and 506 men. The pollsters showed them a list of personal attributes and asked them to indicate whether each attribute was generally more true of men or of women. When asked about intelligence, 28% of the men thought men were generally more intelligent, but only 14% of the women agreed. Let's create a 95% confidence interval for the parameter. All right, so let's go ahead and if we want to build this confidence interval, we first have to make sure the 4 conditions are met. So let me find, here we go, condition section. We need to check, as always, randomization first. Well, in this case, we are told the men and women from each sample are drawn randomly. Or really, that's an awkward way to word it. The men and women are drawn randomly for each sample of size 506 and 520 that we have. Okay, so we've checked that off. And again, we checked it doubly. Rather than just for one sample, we checked it for two. After randomization, you have the 10% condition, as we've seen come up for every sample distribution we have worked with, both for means and for proportions. We've worked with the 10% condition, just as we worked with randomization every time. So these two right here, you'll have to do for just about any sort of test, confidence interval, distribution question you would answer next test. Those are going to be there regardless. 10% condition. All right, so among the women, we have 520 women. It's certainly less than 10% of all women. And that 506 men, certainly less than 10% of all men. All right, so we've checked off the 10% condition. Let's check next for independence. We're not really told, again, how the test was conducted, aside from the fact that it was a simple random sample, or a random sample rather. So we just need to say that we're assuming pollsters, those who were polled, were interviewed in such a way that individuals' views were not affected. Okay, so independence we've checked, and then the last one we need to be aware of is the success failure condition, which I'll abbreviate S/F here. Please, on the test, well, I'll just do this now. It doesn't save me that much time anyway. Success failure. That's how I want you to write this condition. I had students going into the AP exam who were still writing S/F last year. That doesn't mean anything to the AP grader. It makes sense in class, and I'm sure they see it a lot, but that's not the name of the condition. I think you might be able to get away with abbreviating independence in depth, but I probably wouldn't do that either. Probably write independence. Go for being concise, but fewer abbreviations when it comes down to test time, either in my class or on the AP exam, the better in general, because it gets ambiguous fast. We've got a lot of things that you can abbreviate in similar ways in this class. Success failure. So for the men first, obviously for the men first, no. We've got checking. Well, we had a 28%. 28% of the men thought men were generally more intelligent, so we're going to multiply that probability of success, quote unquote. I think most of us could agree that that might be failure. 28% times 506, the sample size of men we interviewed. That's equal to 142, which is certainly greater than 10. Similarly for failure, quote unquote, because again, this is probably the healthier view to have. 72% times 506 equals to 364, certainly greater than 10. All right, so for women next, we're checking that we have at least 10 quote-unquote successes, at least 10 quote-unquote failures. 0.14 times 520, different sample size here. Don't get the two confused. I saw students last year confuse which sample they were working with. Well, the men, we had 506 of the men, we had 520 of the women, so you got to keep track of those. So we've got, that comes out to be 73 women who were quote-unquote successful here, but certainly greater than 10. And converse of that, or the complement rather, 0.86 times the 520 gives you 447, that makes sense, which is greater than 10. Okay, so all the conditions have been met, and here is the statistic we're building a confidence interval for. Notice I said, and I want this to be clear, we're not talking, when we build this confidence interval, of what is this, a single proportion of men or a single proportion of women doing. We've done that in the past. Now our statistic, the quote-unquote population proportion that we're building a confidence interval around, this confidence interval is for the true proportion of men who think that men are generally more intelligent, minus the true proportion of women who think that men are generally more intelligent. This is what we're trying to estimate with the samples that we have of size 506 and 520. All right, so let's go ahead and build this. So we wrote conditions here. Let's write mechanics below. And for this, the confidence interval, I'll rewrite this. You saw this last slide. Yes, it's being redundant, but I think that it's valuable for you to for you to see what is going on here at least once. Twice is good. P hat M minus P hat F. So we're saying sample proportion of men who thought men are generally more intelligent minus the sample proportion of women who thought men are generally more intelligent, plus or minus the z-score. This again comes from the confidence interval we're using, which we were told was 95%. So you might remember at a 95% confidence interval, level rather, you are working with a z-score 1.96, and I'll show that in just a second, times standard error of p hat m minus p hat f. Okay, so let's go ahead and fill in this piece here. That's not hard to do. We were told the sample proportion of men who think men are generally more intelligent is 0.28. For women, it was 0.14. Okay, well, if I'm going to sort of quote-unquote abbreviate this bell curve. This bell curve is centered on that p hat m minus p hat f. So this right here, that line I just drew, would be 0.14 coming from 0.28 minus 0.14. We don't really need that per se. We just need to know what the z-score is. So we are building a 95% confidence level. We need then inverse norm right here to know how many standard deviations out we are at 0.975. I did not leave myself alone. 0.97. Oh, that's a 5.3 weird thing. Okay, 0.975 is what we have there. I'm just going to close that, 0.975. That gives you a z-score of 1.96. So we're filling out this confidence interval, no sweat, 1.96 times our standard error. Let's go to the left here for that, the standard error of, nope, I think that's going to be silly. Let's go down to the right. Standard error of this difference in sample proportions equals square root of, we're going to use, remember, sample proportion 1, that's, or sample proportion of success, which is 0.28 times 0.72. We had 28% of the men thinking men are generally more intelligent among this sample of size 506. There's your N1 coming from last slide. Plus, sample proportion of success among the women was 0.14, obviously lower, times 0.86, all over sample size of 520. Simplify this out, and you get 0.025 for your standard error. So this is valuable, and then the 0.28 minus 0.14 we've already filled in, also valuable to get the confidence interval for the true difference in proportion of attribution of intelligence to men among men versus women. Men versus women. Men minus the women here. So standard error we said was 0.025. Simplify this out, and you find that this difference, again, is centered on 0.14 plus or minus 0.049, which is, I mean, that 0.049 is approximately 0.05. So it is more or less that we believe with 95% confidence, and I'll write this out in just a second, that the true proportion of men who believe men are generally more intelligent than the true proportion of women who believe men are generally more intelligent lies in the interval 9% to 19%. All right, so again, let's put this out in writing here. So conclusion. Is that with 95% confidence, the proportion, this is the true proportion, not a sample proportion, the proportion of American men who think, just at all, intelligence applies more to men than women is 9% to 19% higher than the proportion, I know this is wordy, but welcome to statistics, is 9 to 19% higher than the proportion of American women who think that about men. All right, so really, again, the math is nothing new. But the new tool is that we can now take samples from two different populations, and as long as 4 conditions are met, we can talk about what we believe the true difference between the population proportion from each different population to be, which is kind of a powerful idea. I think we're going to see some kind of cool problems worked out using this math, or using this stats. It's hardly math. And I will see you guys next time. Have a great Monday.